times in our previous analysis, we have used time invariance and homogeneity properties of the solutions coming from an LTI circuit. In this lecture, we will see through some very simple examples that such nice properties in general are lost when the circuit is no longer LTI. Okay. But first, let's remember once again what those properties were. Okay. Consider the three cases, okay, or three experiments, okay, say, that we perform with this simplest first order circuit. No input, only a capacitor and a resistor connected in series. Okay. Okay, this is the setup for the experiment 1. Let's say this is the setup for experiment 2. Okay. We're using the same setup, and this is setup, let's say, for experiment 3. CR. This is VC2. Indicate the difference between the outputs of the different experiments. Let's use this notation, okay, for the other experiments. This is VC, this is VC hat, this is VC tilde. Now this circuit or this experiment, we start from initial condition V0, and clearly this is what we record. V0 e to the minus t over time constant. Okay. VC hat. Alright, so now this experiment is such that we use the same initial condition as the first experiment, but we start the experiment at a later time. Okay. And in the third experiment, we start at t equals 0. We use the same initial time, but we use a scaled version of the initial condition of the first experiment, namely VC0 equals some constant, some scalar times this initial condition V0. Okay. Now, if you know the solution to the first experiment, you don't have to perform the remaining two experiments, because the circuit is LTI, and you can use time-invariance and homogeneity to directly write down the solutions for the two other cases. Okay. Now, for this experiment, or for this circuit, we have VC hat of t, V0 e to the minus t minus pi over RC. Okay, so this is the shifted version of the first experiment, because the initial time is shifted. And as for this guy, initial time stays the same, but the initial condition is scaled. Therefore, what you have to do is you have to scale the solution. So VC tilde t equals lambda times the solution that you obtained for the first case. V0 e to the minus t over RC. Okay. So, for an LTI circuit, therefore we have VC0. If you shift the initial time, all you have to do is shift the solution. VC hat t equals, take the original solution and shift it pi seconds to the right. And this is time invariance, or the result of time invariance. Okay. And for the second experiment, or third experiment, VC tilde equals lambda VC0. If the initial condition is scaled, then the solution can also be scaled. VC tilde t equals lambda VC t. And that we call homogeneity property. Now we're going to see through some simple examples that these very nice properties are no longer guaranteed to hold if the circuit is not LTI. Consider the case, again an RC case, but this time R is not LTI, it's not an LTI resistor, but an LTV resistor, okay, Time-Invariance. Plus minus VC. Suppose the capacitance is 1 farad. The current is I, and this is the voltage of our LTV resistor. And the current voltage characteristics is given as 1 plus 1/2 cosine t I. Okay. Therefore, the conductance of this LTV resistor goes back and forth between 1/2 mhos and 1.5 mhos. Okay. Now, the initial condition, suppose, is 1 volt. Question is, what's VCT? So let's first solve this LTV circuit. Here is the solution. Well, what we do is how we obtain solutions. We obtain the differential equation and hope that we can solve it in general. It's not guaranteed that we have a solution, okay, or the exact solution. What we do is we resort to numerical methods or the computer help. But this is a very special and first very simple example, so we will be able to, in fact, obtain the exact solution. So, let's start from determining the equation of the capacitor. C dVc, and C is 1, equals capacitor current. IC, okay, direction, that. And by KCL, IC is minus I. Okay. And that's minus, okay, I is V times denominator, and V is VC, therefore we have 1 plus 1/2 cosine T VC. Okay. So let's try to obtain capacitor voltage for that time-varying linear differential equation. So we can write, express that differential equation in the following form: dVc over Vc equals minus 1 plus 1/2 cosine t dt. Then integrating both sides, dVc Vc equals minus 1 plus 1/2 cosine t dt, and that yields ln Vc equals minus t plus 1/2 sine t plus some constant. And that constant will be determined eventually by the initial condition. Therefore, VCT must equal, taking exponentials of both sides, we have K e to the minus t plus 1/2 sine t. And VC0 is given to be 1 volt. That implies plugging t equals 0. This disappears, this is 0. So we have e to the 0, which is 1. So k must equal the initial condition. Hence, k equals 1. Therefore, capacitor voltage equals e to the minus t plus 1/2 sine t volts. Okay. Now let's consider the same circuit, the same initial conditions, but at a later time. So how about this case? Plus minus V 1F. This is our capacitor voltage. Now, this is our, let's say, second experiment. Therefore, we're indicating capacitor voltage with a slightly different notation, VC hat. And we have V equals 1/1 plus 1/2 cosine t pi. VC hat pi. Now, pi we take as our initial time, and the initial condition is still the same as the first experiment. The question now is, what's VC hat t for future times? By future we mean times greater than or equal to pi. Now again, we have the same form for the solution, some constant times e to the this piece. So we see hat t equals k, let's call it k hat, okay, the unknown of the solution, minus t plus 1/2 sine t volts. Now what's k hat? For that we use the initial condition constant. Okay. VC hat pi is due to be 1 volt. Therefore, plug in t equals pi. Here we have sine of pi is 0, so we have e to the minus pi times k hat equals 1. Okay, so k hat must be e to the pi. K hat equals e to the 3.14, 15, and so on. Okay. Now, what's VC hat t? VC hat t equals k hat, which now is computed to be e to the pi, and e to the minus t plus 1/2 sine t. And that can be written as e to the minus t minus pi plus 1/2 sine t volts. Okay. We have VC t here, and we have the solution for the same circuit, for the same initial condition, but starting at a later time. By comparing these two solutions, we immediately see that time invariance property is lost. Okay. So that's the lesson that we take from this example. Note that the time invariance property is lost. In other words, that solution is not just a simple shifted version of this solution. Okay, you cannot obtain that solution by shifting. Okay. That is, in other words, VC hat of t does not equal VC shifted by pi units. So that's a simple circuit. That's linear but time varying. Now let's look at a time invariant but nonlinear circuit. This time we will be losing the homogeneity property. Nonlinear resistor. Let's use the same topology, capacitor connected to resistor. Okay. And the IV characteristics of our nonlinear resistor is given in that relation. And VC0 is something that's something positive. The question is, what's VCT for future times t greater than equal to 0? Again, we're going to write down, we're going to obtain the differential equation and try to solve in general nonlinear differential equations. Do not admit exact solutions. We don't know how to solve them exactly. So what we do is we use numerical methods or simulations or whatever help. Yeah, but for this simple example, we will be able to obtain solution explicitly. Okay, so again, let's start from the terminal equation of the capacitor and obtain the differential equation. dVc equals IC, because the capacitance is 1 farads. That's minus I, and that's minus VQ, and that's minus VC cube. Okay, because V and VC, they are the same voltage. Therefore, and this operator is d over dt, hence we can write minus dVc VC cube equals dt. Then integrating both sides yields 1/2 VC to the minus 2 equals t plus some constant to be determined by the initial condition. Hence, VCT will have this form, 1 over 2t plus k, and then we take the square root. Okay, so that's the formal solution. And if you apply the initial condition constraint, VC0 equals V0, that yields 1 over square root of k equals V0, hence k equals 1 over V0 squared. This allows us to write explicitly the solution in terms of the initial condition as V0 over 1 plus 2 V0 squared t. For t positive. Now, if you start, so we started the circuit from initial condition V0. If you start from a scaled version of the initial condition, lambda times V0, for an LTI circuit, what we expect is lambda times VCT. But for a nonlinear circuit, that's not the case. So let's put that down as our second remark. Note that this time the homogeneity property is lost. And to see that, just start the circuit from a different initial condition. Okay, this is the original initial condition V0, and let's start circuit from lambda times V0, and let's call the solution starting from this initial condition as Vc hat. Then in that case, by just simply plugging in lambda V0 instead of V0 here, you can obtain Vc hat of t, and then you can compare Vct and Vc hat t, and it's easy to see that Vc hat of t is not equal to lambda times Vct. Okay. You would have the equality for an LTI circuit, but for a nonlinear circuit, the equality is broken, or homogeneity is broken.